Hi, I'm Milinda Jayamaha and we are here to present Lab 3 Part 1. So in Lab 3 Part 1, we are basically supposed to build this circuit which consists of one D-type flip-flop and two JK flip-flops. So we are using a 74374 for the D-type, 1017 use the two JK flip-flops and a 74HC86 for the OR gate. So basically these are our pin numbers, and these are our input equations. And then basically these are truth table for the condition where Ka and Kv equals to 1. And then this shows our truth table for when Kv and Ka are 0. Okay, so this is our state transition diagram. So this state transition diagram is basically shows when Ka and Kv are both 1. So as you can see here. Yeah, so basically this follows the same outer pattern of the loop. Now we are going to check for inner transition conditions. So basically I have to turn Ka and Kv both off. Yeah, and as you can see here, basically what happens is it follows the inner loop. So basically it goes from this state to this state and this state to this state, and then what happens is it continues cycle between these two states, as you can see. It goes from 1 1 1 to 0 1 1. So again turn it on and off. Yeah, so basically it switches back to the inner loop. So once I again turn both on, it follows the old pattern. Yeah, so now what happens is basically following another transition from here to here and from here to here, and then so yeah, so basically once you, as you can see, when you turn K and Kv both off, it will follow the inner set of transition, and once you turn it back on, it will again go back to the outer transitions. Okay. Hi, I'm Milinda Jayamaha and I'll be introducing Lab 3 Part 2 and the second circuit because Ronald has already shown the first circuit. So basically this circuit involves an 8-to-1 multiplexer and a single gate using a mux and an inverter. So this is our circuit diagram which is drawn, and you can see the pinouts over here. And basically this is our truth table. So there are 16 different states, and then we are going to show that in the demonstration. Okay. So initially, since the 4 inputs are 0, the output is 0, and then basically this indicates our output module, and currently it's 0. Now we make D1, it's 0, okay, and then we make C1, it's still 0, and then we make C and D1, the output becomes 1, and next we make B1, the output is 1. Then we make D1, the output is 1. And then we make B, C and D all 1. It turns 0. Then our next thing is where A is 1. So we turn off all the other inputs. Press A, it turns 1. Then we make D1, it turns 0. Okay. Then our next stage is we make C1, it's 1. Then we make A1, B0, C1 and D1, it's 1. Then our next thing is to make A and B 1, and as you can see it's 0. And then we make A1, B1 and D1 1. And then we make ABC 1. We make ABC 1 is 1. Okay. The last state is A1, B1, C1, D1, and it should be 0. So we're going to do that. We're going to turn A1, we're going to turn B1, turn C1, and they're going to turn D1, and as you can see it's 0. So basically we have shown that all the 16 states correspond to each other, and it's proved in the demonstration. That's all. Thank you.
Hi, I'm Ronald, and today I'll be demonstrating to you part 2 of Lab 3 in 8-bit light chaser. So as shown below, the circuit has been built using two ICs, the 74HC161 and the 74HC138. Both the ICs have been lined up together side by side so that the output can be seen through the LED shown below. When the switch is pressed off, the circuit is in idle, and when the switch is pressed in, the circuit demonstrates the expected outcome. So the 74HC161, which is this chip, acts as the circuit, that's the counter. So the 74HC138, that's this chip, that acts as the decoder. this is a 1 of 8 decoder, and the output of the decoder is given out to the LED. So the LED outcasts the expected output. So whenever the switch is pressed and not pressed, the output is given through the LEDs. Thank you.
Hi, I'm Milinda, Jayamaha, and I'll be presenting Lab 3 Part 3. So basically for this part, we have to use a K-map to determine the hazard in this particular circuit. So what we did was we drew the K-map, and then once you draw the K-map, we get the output is 1 if the expression is A bar, A B bar plus BC. So once you draw the K-map, so basically you will see that there is a redundant loop over here. So basically the redundant loop includes the expression ABC. So once you inspect ABC, the transition is as shown. So 111 transitions to 101. So basically input B is the issue here. So basically B goes from 1 to 0. So as we're going to show on the oscilloscope now, this is our input A and this is our input C, and B goes to the clock input. So as you can see on the oscilloscope, this is input B, and then currently the output is 0. So basically now once you press input A, you're going to get a positive blockage. So you can see here. Yeah. So basically A goes on and off according to the clock, the output. And then when you press C, you see the same thing. Because according to the expression of F. So now we're going to inspect the hazard. We're going to turn on both A and C. Yeah. So basically we're just going to move this to get a clear picture. Yeah. So basically, as you can see here, the input B is at the bottom, so you can see a comparison. So what is happening here is the output briefly dips to 0 and then goes back up. So basically, these little shades over here are basically due to the noise picked up by the circuit. But regardless of that, you can basically see that the output basically dips to 0 and then goes back up to 1. Basically, thus proving our static band hazard.
Hi, I'm Ronald, and I'll be explaining and demonstrating to you part 3 of Lab 3. So as you can see here, we have implemented the circuit described in the part 3 over here. So the following circuit implements the hazard as shown over here. So the hazard is prevented by implementing the cover AC. So by implementing this cover, the hazard is prevented. So to prevent the hazard, we have implemented it using the circuit shown here below. So this switch here will be representing A, and this switch will be representing C. So when I click on A, you can see the normal wave output is shown. So as soon as I off A, now I'll be demonstrating to you the cover. So when I on the cover, the hazard is completely gone. So the signal is a constant DC signal, and the hazard has been completely prevented using the cover described in this circuit. So using this circuit, we have prevented the hazard from occurring using the 74HC02 and giving it as the input to the 74HC10.